Welcome. Let's go through 1.2.1, and this is the one with the logos that you can see here. So one thing that I like to do is to start with tables, and you can see the first one is 7, the second one is 12, the third one is 17. From that we can get the pattern. We notice that the change is 5, so that will be the slope. It's constant, so therefore we know that it's a linear relationship. Right? And we can look at this two ways. One would be point slope, one would be slope intercept. I'm going to use point slope because we're given some points, but not necessarily the intercept, although we can figure it out. So first thing is, let's say we use the 0.17. We know the slope is equal to 5. So I'll write that in. We know that when x is 1, y is 7, so 5 times x minus 1 plus 7. We could test that out to make sure that that works by saying, is it true that 7 is equal to 5 times 1 minus 1 plus 7? And when we simplify that, we see that it's true. It would also work for other values of x. So let's say we want to do 317. We could say 17 should be equal to 3 minus 1 plus 7, and that's 5 times 2 plus 7, and that's equal to 17. So we know that this is a good equation for it. Makes sense. You could do slope-intercept if you backed up. You could say, oh, since the change is 5, it must, if we go back to 0, it'd have to be 2, and that's true for the equation. However, that's not the pattern. That's not what's really happening here. It doesn't really make sense to have 0. So, but you could use this to figure out how many squares on a 100 league logo. So you could say y equals 5 times 100 plus 2. Or you could use the other one, y equals 5 times x minus 1, so 100 minus 1, okay, plus 7, also equal to 502. That's the linear. The next one is the quadratic. Quadratic, same thing. It's good to make a table, and we notice the change, 7, 21, 35, 49. The second change, 7 plus 14 is 21, and 21, 14 is 35, and 35, 14 is 49. This is constant. So therefore we can say that it is a quadratic, and it's quadratic because the second change is constant. Now, then the question is, what is a recursive equation? And for recursive, we need to be able to understand what the change is and model that. This is a linear pattern here. The change to get to the first one was 7. The change to get to the second one was 21. The change to get to the third one was 35. If we look at this, we notice that the slope is constant. It's 14. So therefore, you can model the change with a linear equation here. Okay? And when we look at that, we can use point slope, and you'll see it right here. 14, that's the slope of n minus 7. Okay? And that is a way to model this. And that one is actually, if you were to do slope-intercept and you were to go back another 14, you would have negative 7, right? And that's where this comes from, this 14n minus 7. The explicit function would be 7n squared, right? And that, if that makes sense if you look at it, there's 7 times 1 squared, 7 times 2 squared, 7 times 3 squared. Okay, and that's how we get to 7, 28, 63, 112. The last thing is compare the models. Well, constant slope for linear, whereas it's a linear pattern of change for the quadratic, where it's constant for the linear. Other things that we can notice here is the second difference is the same, whereas here the first difference is the same. Okay. Other things, if you graphed it, a straight line for the linear, a parabola for quadratic would be another thing that you could see also. The equations are different. Here you're using mx plus b, or point slope, which is m times x minus a value, where x1 and y1 is a point. Here your equation is going to be different. Some number times x squared plus bx plus c. So those are some of the differences here.